In this talk, I'm going to present an S&T procedure for bit precise reasoning based on ternary propagation-based local search. Our procedure is a generalization of the recent local search approach with respect to constant bits, that is, bits that can be simplified to constant values. This is joint work with Matthias Breiner. But first, let's start with a quick reminder. What is satisfiability modulo theories, or S&T? In essence, this can be boiled down to the following question. Given a first-order logic formula and the combination of theories, is there an assignment to its variable such that this formula evaluates to true? So in this particular example here, we have a formula over the bit vectors and the arrays, and the question here is there an assignment to x such that it evaluates to true? And this is obviously not the case, since the formula is unsatisfiable. In the following, we are going to focus on the theory of fixed-sized bit vectors without quantifiers. The theory of fixed-sized bit vectors is defined over bit vector constants and variables, bit vector operators such as left shift, right shift, bitwise AND, bitwise OR, concatenation, and so on. But most importantly, we have to consider overflow semantics, since arithmetic operators are defined modulo 2 to the power of the bit width. Current state of the art for quantifier-free bit vector formulas is a technique called bit blasting. Bit blasting typically entails rewriting and simplifications on the input formula before it is eagerly reduced to propositional logic and handed to a Satzhover. Bit blasting is surprisingly efficient in practice, mainly due to the fact that Satzhovers nowadays can easily handle millions of variables without breaking a sweat. However, it may suffer from an exponential blowup in the formula size and therefore typically does not scale too well for large bit widths. As an example, consider a simple constraint x times y is equal to z, where x, y, and z are of size 2. The bit blasted circuit representation is shown here as an anti-inverter graph, where the bottom blue triangles indicate the input bits, the top blue triangle indicates the output bit, circles represent AND gates, and bullets represent NOT gates. If we increase the bit width of this constraint to 8, the circuit representation is already considerably larger. However, if we increase it to 32, you can't even make out a single gate anymore. And 32 bits is not even considered a large bit width. So what does this mean for us in practice? Yes, bit blasting is efficient. However, for the cases where it isn't, we need alternative approaches. And the procedure I'm going to present in this talk is such an alternative approach. It is a generalization of the propagation-based local search procedure that we presented in 2016 at CAF. Propagation-based local search, as the name implies, is a local search procedure that is based on propagating target values from the output to the inputs. It lifts the concept of backtracing from ATPG to the word level and does not require bit blasting or a Satzhover. We assume that the input formula is satisfiable and represent it as directed acyclic graph with a single root R. We start off with an initial assignment that does not satisfy the input formula, that is, R evaluates to false, and now assume that this root R has target value 1, indicated by this squiggly arrow. We now propagate this target value along a single path towards an input, and we repeat this process iteratively until we reach a satisfying assignment. This approach is orthogonal to bit blasting in the sense that it cannot compete with bit blasting but complements it. It is incomplete in the sense that it is not able to determine unsatisfiability, which is actually expected for local search. However, for satisfiable instances, it is complete in the sense of probabilistically approximately complete, which means that it is guaranteed to eventually find a solution if there is one. The main weakness of the original propagation-based local search procedure, however, is its obliviousness to constant bits. Constant bits are bits that can be simplified to constant values independently from the current assignment. When down propagating target values, the original procedure does not consider such constant bits, and this may result in a lot of redundant propagation work when target values that can never be assumed due to constant bits are propagated. Our ternary propagation-based local search procedure addresses this weakness by generalizing the original procedure to ternary values with respect to constant bits. We define symbolic conditions to determine if value propagation with respect to such constant bits is possible, and further extend the procedure with bound tightening heuristics for inequality constraints. Our procedure is a non-deterministic algorithm, and its main components are propagation path selection and propagation value selection. These two components are also the main sources of non-determinism of our procedure. Target values are down-propagated starting from the root with respect to constant bits. This constant bit information is pre-computed once upfront before the actual local search procedure is initiated. For this, we utilize the AIG representation of the input formula and determine constant bits as AND gates that can be simplified to constants, which are then mapped back to the word level. We maintain this constant bit information as a ternary bit vector for each node in the DAG. We represent the ternary bit vector x as a pair of binary bit vectors x low and x high, where x low and x high determine the minimum and maximum values of x. Bits with undetermined value are set to 0 in x low and to 1 in x high, and constant bits have the same value in both. We additionally only consider valid x low x high pairs, that is, we don't allow a bit that is 1 in x low to be 0 in x high. This is enforced by the constraint not x low or x high must be equal to 1s. In the example here below, we have a bit vector of size 4, where the least significant bit is constant 0 and all other bits are undetermined. Zooming in on value selection, we typically compute propagation values as inverse values. An inverse value for an operand is a value that allows to assume the target value immediately without changing the assignment of other operands. Computing inverse values, however, is not always possible, and in cases where it isn't, we apply a less strict notion that we refer to as consistent values. A consistent value is a value that allows to assume the target value eventually after changing the assignment of other inputs if necessary. As an example, consider a bitwise AND operation with current assignment 0 and target value 2, and assume that the right operand has value 2. Possible inverse values for the left operand are 2 and 3. However, if we change the assignment of the right operand to 1, there is no inverse value for the left operand, but 2 and 3 are consistent values. Note that every inverse value is also consistent, and further, if we do not consider constant bits, consistent value computation is always possible. Now, throwing constant bits into the mix just means that this restricts our choice of possible values further. For example, here on the left-hand side, if we assume that the least significant bit of the left operand is constant 0, then the only possible inverse value for the left operand is 2. However, as a consequence, when considering constant bits, it's not always possible to find the consistent value anymore. That means that value propagation is now always conditional and can only be performed if at least the condition for consistent value computation is true. We determine if value propagation is possible by defining symbolic invertibility and consistency conditions, and if it's not even possible to compute a consistent value, we break the propagation and restart from the root. Zooming in on propagation path selection, we generalize what we refer to as the notion of essential inputs with respect to constant bits. The notion of essential inputs lifts the notion of controlling inputs from the bit level to the word level. That is, an input is essential under the current assignment if it does not allow to assume a given target value no matter which value is assigned to the other input. In our example here on the right-hand side, again assume that we have a bitwise AND operation with current assignment 0 and target value 2, and assume that the left operand has value 0 and the right operand has value 3. So in this case, the left operand is essential because it forces the AND operation to be 0, no matter which assignment we assign to the right operand. The right operand, on the other hand, is not essential. In general, we select essential inputs over non-essential inputs. As an interesting observation, an input is essential if there does not exist an inverse value for the other input. We utilize invertibility conditions to determine if an input is essential. We define invertibility and consistency conditions with respect to constant bits for our set of considered operators and utilize them for propagation path and value selection. Given a bit vector constraint x of s is equal to t, where x is a ternary bit vector that represents constant bits of the operand to solve for, t is the target value, and s is the value of the other operand, if any. For invertibility conditions, we have that for all x, s, and t, the invertibility condition evaluates to true if and only if there exists a value y for x such that the given constraint evaluates to true and constant bits in x match the corresponding bits in y. Similarly, for the consistency conditions, we have that for all x and t, the consistency condition evaluates to true even only if there exists a value y for x and a value s for the other operand, such that the given constraint evaluates to true, and again, constant bits in x match the corresponding bits in y. For the bitwise AND constraint from our previous example, the invertibility condition and the consistency condition are defined as given below. Remember that when not considering constant bits, the consistency condition is always true, since it is always possible to find a consistent value. For the invertibility condition, when not considering constant bits, the invertibility condition is reduced to the orange part of the given invertibility condition. Putting all pieces together, let's quickly go through a simple example that also motivates why our ternary propagation-based local search procedure significantly reduces propagation overhead compared to the original procedure. Let's assume that we have a constraint v times v and 10 is 4, and assume that first we apply the original propagation-based local search procedure, which does not consider bits that can be simplified to constant values. Let's assume that we start with an initial assignment where we assign v to 0, and as a result the root is false and the input formula is not satisfied. We now assume that the target value for the root is true and propagate this target value down to the multiplication by computing an inverse value. Both operands of the multiplication are 0 and therefore essential, and we randomly pick the right one. We pick one of the possible consistent values and continue propagation. Now for v, there doesn't exist an inverse value given the current target value, and we pick one of the possible consistent values. We assign v to the selected consistent value, evaluate the current assignment, and the root is still false. We again assume target value true for the root, propagate it down to the multiplication. Now both operands are not essential, we randomly pick the left one and compute an inverse value for v. We pick one of the possible inverse values for v and reach a satisfying assignment. Now lifting this procedure to ternary propagation-based local search, we determine that the multiplication operation has a least significant bit that is constant 0, and the bitwise AND operation has two constant bits that are 0. Starting from the same initial assignment, we again assume that the target value for the root is true, propagate this value down to the multiplication, again determine that both operands for the multiplication are essential, and again pick the right one. But now the number of possible consistent value is significantly reduced. We pick one and are able to compute an inverse value for v. And this inverse value already satisfies the input formula, and we are done. As you can see from the previous example, generalizing propagation-based local search with respect to constant bits allows us to propagate more precise values, since we exclude propagation values that can never be assumed. However, propagation value selection can still be challenging if the number of possible values is large. And very often, we can significantly restrict the choice of possible values even further. For example, consider a formula x is less than 7 and x is greater than 5. Since we only consider a single path when down propagating target values, both for the left and right inequality constraint, the range of possible inverse values is considerably large. But actually, when considering both constraints on x, the range can be reduced to two possible values. We therefore extended our procedure with a heuristic for inverse value computation, where we compute bounds for x based on currently satisfied top-level inequalities on x. If the bounds that we compute is invalid, we conclude that there is no inverse value for x and compute a regular consistent value. Note that we do not apply this heuristic for consistent value computation, since this would affect completeness of our procedure. As an additional optimization, we further introduce special handling for inequalities over sign and zero extension operations, where we derive bounds based on the prefix of the extension operation. We implemented our procedure in our new SMTs over Bitmutzler and compare it against the original propagation-based local search procedure as a baseline. We evaluate 3 configurations on all benchmarks in the quantifier-free bit-vector logic of SMTlib with status SAT. We compare them over 20 runs with different seeds for the random number generator and a time limit of 60 seconds. Configuration-Base implements the original propagation-based local search procedure. Configuration-Prop-C implements our ternary propagation-based local search generalization, and configuration prop CB plus extends configuration prop C with our bond tightening heuristic. Compared to base, our procedure improves considerably, with configuration prop C gaining plus 120 median solved instances. As expected, redundant work is significantly decreased, with a reduction of 70% in terms of moves and 63% in terms of propagations on commonly solved instances. When enabling our bond tightening heuristic, the number of solved instances increases by another 400 median instances. As mentioned before, we utilize our procedure to complement bit blasting, and for this we combine it with bit blasting in a sequential portfolio configuration. That is, we first run local search until a fixed number of propagations is reached, and then fall back to bit blasting if no solution was found. We implemented this configuration in our SMT solver BitWurzler and evaluate its performance with all 4 SAT-solver backends that are supported by BitWurzler on all quantifier-free bit vector benchmarks in SMT-lib with a time limit of 1200 seconds. All of these SAT solvers are current state-of-the-art solvers, and KeySat even won the SAT competition this year. We show our results as scatter plots, where all dots below the diagonal indicate an improvement of our approach over bit blasting. As you can see, our approach clearly improves over pure bit blasting on satisfiable instances, and the overhead introduced for unsatisfiable instances is negligible. To conclude, we presented a generalization of propagation-based local search for quantifier-free bit vector formulas with respect to constant bits. We showed that our approach significantly reduces redundant work and improves performance over the original procedure and pure bit blasting. We determined symbolic invertibility and consistency conditions for a representative set of bit vector operators and verified these conditions for bit widths up to 65 bits. We leave bit width independent proofs of correctness for these conditions to future work. We further introduced a simple bond tightening heuristic for computing inverse values over inequality literals, which considerably improves performance. We leave generalizing this heuristic to be applied for all operators, not only inequality literals, to future work. Another interesting avenue for future work is a tighter integration of local search with bit blasting in order to share information between these 2 procedures. A possible direction for this is to explore hybrid approaches.